de Madan. Pour cette thèse donc intitulée Optimization of a Catalytic Process for CO2 Purification from Oxycombustion. Alors cette thèse a été réalisée en cotutelle entre l'Université du Littoral Côte et l'Université de Mons, France et Belgique. Thèse en cotutelle et le jury est mixte. Je vais vous en présenter les différents membres. Nous avons d'abord deux rapportrices, donc Madame Valérie Chamber, professeure à l'Université de Haute-Alsace, Madame Sabine Vallange, maître de conférence HDR à l'Université de Poitiers. Ensuite, deux examinateurs, même trois. Monsieur Thierry Vizard de Beaucarmé, professeur à l'Université libre de Bruxelles, Monsieur Sébastien Royer, professeur à l'Université de Lille, et Monsieur André de Crolly, professeur à l'Université de Mons. Je citerai ensuite les trois co-directeurs de cette thèse. Monsieur Guy de Werel, donc de l'Université de Mons, professeur, Stéphane Stieffer, professeur aussi à l'ULCO, ainsi que Christophe Poupin, maître de conférence, Université de l'ULCO. Et enfin, pour ma part, donc j'ai le plaisir de présider ce jury, donc Diane Thomas, professeure de l'Université de Mons. Alors, quand même pour vous expliquer que, étant donné que cette thèse est en co-tutelle, il y a déjà eu une défense privée, comme on l'appelle en Belgique, une défense privée qui s'est d'ailleurs déroulée à Mons, où tous les membres du jury ici présents ont déjà posé énormément de questions. C'est vraiment la défense majeure, je veux dire, qui dure très longtemps et à l'issue de laquelle, eh bien, Madan a été autorisée à présenter cette défense publique. Mais donc, je propose d'écouter pour une quarantaine de minutes l'exposé de Madan et ensuite nous aurons encore diverses questions à poser à notre candidat docteur.
Bien, merci. Bien.
Oui. Oui, si vous voulez bien couper vos portables pour ne pas perturber l'exposé de Madan. Je pense que certaines personnes nous entendent à distance. J'imagine que la qualité est bonne. L'exposé de Madan se fera en anglais ainsi que l'échange questions-réponses.
Et si vous voulez, est-ce que vous voulez des techniques?
Bonjour tout le monde. Good morning, everyone. Welcome to my thesis presentation. So in this presentation, I will be discussing about my research work that I concluded with the Université de Mons and Université du Littoral Côte. The title of my thesis is Optimization of a Catalytic Process for CO2 Purification from Oxycombustion. So in this presentation, we have four parts. The first part of the presentation, I will be speaking about the thesis background. So briefly about what is CO2 purification and our proposal, how to achieve the CO2 purification in the industrial scale. The second part of the presentation will be development of catalytic material for our application. So I will show you the strategy that we follow to optimize the material composition and the process for the catalytic application. In the third part of the presentation, I will be showing the development of a kinetic model for our reaction system, the process, the methodology that we follow to derive the reaction rate equation, so on and so forth. And finally, I will give my concluding remarks based on this presentation and some of the future perspectives related to my work. So, regarding carbon dioxide, we all know that carbon dioxide has become a global threat to our planet. Currently, we have around 40 gigatons of CO2 emitted from the anthropogenic sources, and 23% of this global CO2 emissions are from the industrial sector. It is only after the power sector which accounts for 40% of the CO2 emissions. Because of the CO2 emissions, we have the effect called the global warming, and which leads to the rise in the global temperature. Currently, the rate of rise is 0.18 degrees Celsius per decade, which is doubled since 1981. Because of this increase in the global temperature, we have melting of the polar ice caps, leading to the increase in the sea level. Currently, the rate of decrease of the polar ice is 420 billion metric tons per year. It is combined, it's the polar ice cap from the Greenland and Antarctica combined. So how to deal with this CO2 emissions? So before knowing the solutions for carbon footprint reduction, it is important to know the type of emissions we have in our sectors. The first part of emissions is energy-related emissions. So these are the emissions, carbon dioxide emissions that we get from industries during the energy consumption. So these emissions can be mitigated by using renewable sources of energies like bioenergy or wind or solar and so on. The second set of emissions that we get is the process-related emissions. So these emissions occur during the industrial process. So it's a part of the process, and it is difficult to mitigate it by just switching to these renewable energies. So for example, on this slide, we have three different industries: cement, aluminum, and ammonia. So here you can see that 65% of the cement industry related emissions, CO2 emissions, are from the process itself, while it is 40% for the aluminium and 30% for the ammonia. So it depends on the industry, but we still have process emissions. So how to mitigate this process emissions? So normally the flue gases coming out from the CO2 emitting source or the industries can pass down through a carbon capture unit. So normally the flue gas consists of a CO2 concentration less than 30. And once it is captured using certain absorbents, could be solid or liquid, depending on the process, we can have a CO2 rich gas stream, which can either be stored under the geological structures or can be used to prepare some renewable fuels or chemical intermediates. There is another process called oxycombustion, where in the process we use nearly pure oxygen, as a result of which we have a very high concentration of CO2 in the flue gas, which is generally higher than 80%. And this oxycombustion can bypass the carbon capture, can bypass the CO2 capture and pass through a CO2 purification unit before being sent for geological storage or use for renewable fuels and chemical intermediates. This whole system in general is termed as the Carbon Capture Utilization and Storage Unit, or CCUS, that is popularly known as. However, in this flue gas of from the industry doesn't only contain CO2. It is a mixture of different other gases like carbon monoxides, oxides of nitrogen, oxides of sulfur, water, oxygen, CO, and nitrogen. So in this work, we were focusing more on NOx, the oxides of nitrogen, which predominantly contains nitrogen monoxide. So in NOx, so when we have NOx in the flue gas, it can leak. If we don't remove it from the flue gas, then we have a risk of leakage from geological storage after the storage of the CO2. So this leakage can be toxic for the environment. The second thing with the NOx, the detrimental effect, is the reaction during the carbon capture process. So the NOx can react with our absorbing solvent, which is generally amine-based solvents, and this degrade the amine solvent and leads to degradation, leads to lowering the efficiency of carbon capture. And finally, NOx is also acidic in nature and can trigger downstream corrosion. Therefore, it is important for us to remove the NOx from the flue gas, which can be done by using an adequate CO2 purification unit. In this work, we propose to use a catalytic reactor that facilitates reactions that would help us to reduce nitrogen monoxide into dinitrogen, which is generally environmentally inert and non-toxic. So let's have a closer look on what happens in this region of the catalytic reaction. So when we have the industrial flue gas coming through or passing through the catalyst, we have the first reaction, which is called the CO-NO reaction, in which the CO acts as a reductant and the nitrogen monoxide is reduced to dinitrogen when it reacts with carbon monoxide, forming CO2 as a byproduct. However, as we saw in our previous slide, that we also have other gas components like water and oxygen, which can also affect this whole catalytic process. For example, in case of oxygen, we can have a reaction of oxygen with carbon monoxide to form carbon dioxide. And at the same time, the oxygen can react with nitrogen monoxide to form nitrogen dioxide. The nitrogen dioxide, again, is a toxic gas, and therefore it should be avoided. The other component that we have in our industrial flue gas is the water. The water can trigger the water gas shift reaction, which is basically the reaction between carbon monoxide CO with water to form CO2 and hydrogen. So the hydrogen here can act as a reductant and help in reducing nitrogen monoxide to dinitrogen N2 and water. Since the conditions of the reaction system is highly harsh, it is important for us to have an adequate catalytic material that is cost effective, first of all, since we are looking for an industrial scale application. It should have a good performance, which means it should have a higher selectivity towards the production of dinitrogen, which is basically non-toxic, instead of forming nitrogen dioxide, as we saw, which is possible because of the presence of excess oxygen in our flue gas. And finally, it needs to be stable, since I told you before that it's a harsh condition and it should run for a long period of time without affecting its catalytic performance. Therefore, it is important to have a stable catalytic material. So to develop the catalytic materials, so I first did extensive bibliographic studies to see what are the metals that are active for the catalytic reaction. Then, based on the bibliographic study, we developed the materials at a lab scale and tested for its catalytic performance. Then the best performing material was chosen and was tested for its stability. And finally, a kinetic model was developed regarding the reaction kinetics taking place in our system. So in this work, we had two types of materials. The first type of catalytic materials we used was the layer double hydroxide. So in the layer double hydroxides, we have two layers of divalent and trivalent metal hydroxides. And we have the anions like carbonates, which is in between in the sandwich. And also we have water molecules, and that is the interlayer water molecules. The other kind of material that we used in this work were perovskites, which generally consist of the A and B side, metal cations in the A and B sides, and we have oxygen in the middle. In this presentation, I will be focusing more on the layer double hydroxides and the catalytically active materials derived from such materials. So in order to optimize the catalytic material, we followed a linear material optimization technique. The first thing that we optimized was the type of treatment gas. So we used the layer double hydroxide and treated it thermally under different type of gases until to form the catalytically active component and see and compare the catalytic performance and choose the best type of treatment gas for our application. The second step was to choose the ratio between active metals. So in this case, we introduced a new active metal into the material, and we played around with the ratio between this active material and investigated the influence on the catalytic performance. And finally, we optimized the treatment temperature. So we treated the catalyst or the parent material at different temperatures, and the catalytically active component that we got at the end we compared its catalytic activity and tried to see the influence of the treatment temperature on the catalytic performance. In this presentation, I will go deeper into this first part of our optimization process, that is the type of the treatment gas. So in case of this study, we chose copper as a starting material based on the literature studies where copper metal was found to be active for such kind of CONO reactions. So at the first place, we first synthesized the LDH structure of the copper aluminum LDH, we call it, and then treat it at a high temperature of 500 degrees Celsius under the flow of different gases like helium, air, CO2, and carbon monoxide diluted with helium at a temperature of 500 degrees Celsius for 4 hours. And at the end, the catalytically active component is known as the mixed oxide is formed. And normally in the further slides, you will see CuRlX as the component that we use. So the nomenclature that we use to designate different materials that we formed during the different treatment gases. In order to see the effect of the treatment gas on the different material properties, so first we did some characterizations. The first characterization was N2 physisorption. So we wanted to see the difference in the textural properties. So what we saw when we compared with the different the specific surface area, the total pore volume, and the pore diameter for the different samples. The first thing that we noticed that not a great influence of the treatment gas was found on the specific surface area of the mixed oxide samples. However, the lowest specific surface area was recorded for the carbon monoxide treated sample, which was supposed to be because of highly reducive gas, that is carbon monoxide diluted in helium, which has resulted in sintering of the particles, and so on. We have a decrease in the specific surface area. The other component that we compared with the samples were the average pore diameter. Here you can see that the average pore diameter lie well within the mesoporous range. So we can say that all our materials were mesoporous. And finally, if we compare all the samples for the total pore volume and average pore diameter, we don't see an appreciable impact of the type of treatment gas on the textural properties of our mixed oxide samples. The second material characterization technique that we used was the XRD in order to know the different crystalline phases that we have in our sample. So at first we did a XRD analysis for our parent material, which is the starting material LDH. So here you can see that we have we reached the LDH structure during our synthesis. However, we also saw some crystalline phases of copper oxide in our starting materials as well. Then upon treatment, for example, we started with carbon monoxide. We see that we had metallic copper on the surface, metallic copper in our sample, carbon monoxide treated sample, which is again due to the highly reductive treatment of carbon monoxide diluted in helium. However, the other materials, that is the helium, air, and carbon dioxide treated sample, all of the samples showed us a similar diffractogram with crystalline peaks regarding the copper oxide species. And the next material characterization technique that we used in our sample for our sample comparison, it was the hydrogen temperature program reduction. In this case, we passed hydrogen gas through 20 milligrams of our sample, and we see the different hydrogen reduction peaks that we get. So these are the hydrogen reduction peaks. So the first low hydrogen reduction peak is generally associated with the reduction of well-dispersed copper-2 species. While if we have a close look on the carbon monoxide treated sample, we also get a peak of reduction at 204 degrees Celsius. This could be because the metallic copper, when was transported from the treatment to the TPR analysis, could have oxidized with the because of the oxygen present in the ambient atmosphere, and therefore they have been oxidized, and these species are now reduced at a lower temperature. The second temperature range that we see here is 250 to 265 degrees Celsius, which is generally associated with the reduction of CO copper oxide clusters. The next, at a higher temperature of 270 to 285 degrees Celsius, is generally the reduction of bulk copper oxide. And finally, the reduction temperature above 300 degrees Celsius is either has a ambiguity. So we have some authors suggesting this to be the reduction of either larger copper oxide species, or it is the reduction of the copper 2 oxide, which has been formed from the reduction of copper O. So we have a two-stage reduction from copper O to copper 2O, and from copper 2O to metallic copper. So two of these possibilities could take place in our case. The next part of the H2 TPR analysis that we studied was the specific hydrogen consumption during the analysis. So we saw that the air and the helium treated samples show us the similar specific hydrogen consumption, which means they have the similar quantity of reducible species in the material. If we see for the carbon monoxide treated sample, we see the lowest hydrogen consumption, which is again associated with the formation of metallic copper that we already saw in the XRD. So we don't have a lot of reducible species available in our material. Therefore, we don't have a huge amount of hydrogen consumption during the analysis. The last part is the carbon monoxide treated sample. So it shows the highest specific hydrogen consumption from all the other samples. So now we compare, after completing the material characterization, we compare the catalytic performance of different mixed oxide samples. For this, we utilized a lab scale reactor. The gas composition that we utilized was adapted from a flue gas from the Brevik cement plant. Sorry. And in the catalyst that we used, it's a sieved. The material form is a sieved ones with a size of 350 to 550 micrometers. We use light of coal, so we play between the temperatures of 50 to 500 degrees Celsius. We work under a reaction pressure of 1 bar and a total flow rate of 200 milliliters per minute. So let's compare the catalytic activity or the performance for the different mixed oxides. So we use two different tests. The one under the dry reaction condition, so without water in the reaction stream, and the other one was with water conditions or the wet reaction condition. So here what you see is a dry reaction condition. So under the dry reaction condition, we don't see an appreciable difference in the CO conversion activity. While in case of the NO conversion activity, we see that for the carbon monoxide, helium, and air treated sample, we see the formation of NO2 only. So we have a high NO2 NO oxidation yield. While in case of the CO2 treated sample, we see that we have less NO2 formation and more NO reduction yield, which is around 38%. While when we see under the wet reaction conditions, so if you look at the CO conversion values, we see that there is a delay in the CO conversion, which is generally associated with the competition for the common active sites during the between the reactant molecules and the water molecules. On the other hand, if we see on the NO conversion activity, we see that we can see some NO reduction yield for all the samples. Here we can conclude that the water triggers a NO reduction, which could be because of the occurrence of a water gas shift-like reaction. However, for us, it is important to see why the carbon dioxide treated sample showed us NO reduction activity under dry reaction condition, while not the air or the helium treated sample show us the same activity. Even if we had the similar diffractograms of the crystalline species of copper oxides, we had the similar TPR profile for all these three samples, and we had the similar textural properties for all these three samples. So in order to further investigate this question, we went with a characterization technique called TGA or thermogravimetric analysis to see what happens during the treatment process. So in this case, we pass the desired gas and through the sample for a temperature range between 25 degrees Celsius to 1000 degrees Celsius. So here are the weight loss curves for both the samples of air and carbon dioxide treated mix oxides. So in the first part of the weight loss, it is associated generally to the loosely bonded carbonates and water molecules. The second region is generally associated with the dehydroxylation and decarbonation process. So you have the the hydroxide from the metal and the carbonate anions, which is present between the layers of the hydroxides being removed during this temperature range. However, for the CO2, under the CO2 gas flow, we see additional weight loss curve, which is generally associated with the loss of more stable bidentate carbonates. So here is the hypothesis that, okay, maybe the CO2 that we use during the treatment process could have reacted with the LDH to form different species of carbonate inside the structure, which could have helped us in the reaction. In order to further investigate or to further support our hypothesis, we did an FTIR analysis under ambient pressure and temperature. So in the FTIR analysis for the CO2 treated sample and the air treated sample, we first see a band at 820, which is generally associated with the stretching vibrations of the metal oxygen bonds. The bands that we see at 1383 and 1485 is generally associated with different forms of different species of carbonates, could be monodentate, bidentate, or polydentate. While at 1073, we see a peak only for the CO2 treated sample, which is in red, which is associated with the bidentate carbonates. So with this analysis, we assured that there is the formation of bidentate carbonates in our mixed oxide sample when it is treated under the flow of carbon dioxide, and therefore could have helped us in NO reduction activity, specifically under the dry reaction condition. So based on the different literature studies for the reaction mechanism, we propose a reaction mechanism that could happen in our reaction system. So in this case, under the dry reaction condition at a temperature of less than 100 degrees Celsius, the nitrogen monoxide from the gas stream can adsorb on the surface of the catalyst to form different nitrate species. However, there could be some adsorption of the carbon monoxide species on the surface of the catalyst, forming different, either the adsorbed CO species or carbonate species on the catalytic surface. When we increase the temperature to more than 100 degrees Celsius, this nitrate species can be replaced by the carbonate species, and these carbonates or the monodentate carbonates generally can dissociate to form the carbon dioxide. At the same time, the nitrogen monoxide that is absorbed on the surface of the sample can react with the oxygen, again coming from our gas stream, to absorb on the catalyst and react with it to form the nitrogen monoxide. This could be because this is why we have nitrogen monoxide in our mixed oxide samples. However, in case of the copper aluminum CO2 sample or the carbon dioxide treated sample, we already have bidentate carbonates available on the surface of our catalyst, and at temperature more than 300 degrees Celsius, the nitrogen monoxide from the gas stream can react with this bidentate carbonates to form the bidentate nitrate species, which are generally active for the NO reduction activity, and they react with the carbon monoxide, which is absorbed on the catalytic surface to form the carbon dioxide and dinitrogen. However, at the same time, there is absorption of nitrogen monoxide on the catalytic surface, which again reacts with the oxygen that is absorbed on the catalytic surface to form the nitrogen dioxide, which is why we see NO oxidation yield under the dry reaction conditions for our CO2 treated sample. Under the wet reaction conditions, there is something interesting happening that we propose. So at first, there is the absorption of the water molecules on the surface of the catalyst. The CO molecule that is already absorbed in the adsorbed state can react with the water molecule to form the formate species, and this formate species can decompose to form the CO2, and there is a formation of an hydrogen, atomic hydrogen on the surface of the catalyst, which can react with the nitrogen monoxide from the gas phase to form the OH, that is the hydroxyl group on the catalyst surface, and an atomic nitrogen. This atomic nitrogen can again interact with another atomic nitrogen which is near to it in order to form the dinitrogen. This is why we see NO reduction activity under the wet reaction condition, and this mechanism is a water gas shift-like mechanism, because we don't see a release of hydrogen in our experimental phase, in the experimental data. Therefore, we suppose that the hydrogen is not released, rather the atomic hydrogen stays on the surface of the catalyst and reacts directly with the nitrogen monoxide from the gas phase to form the dinitrogen. However, in case of the carbon dioxide treated sample, the bidentate carbonates can react with the water molecule to form the formate species. To form the formate species and the hydroxyl group. This formate species are generally inactive for our reaction. And at the same time, we have the water gas shift-like reaction that we already saw in the previous slide, where we form this species that releases the carbon monoxide. We have the formation of the atomic hydrogen on the catalytic surface. We have its reaction with the nitrogen monoxide to form the hydroxyl group and the atomic nitrogen. And the atomic nitrogen interact with the another atomic nitrogen to form the dinitrogen or N2. So we see that the CO2 treatment of our sample gives us a good activity, especially under the dry reaction conditions. So we choose CO2 treatment as the treatment process for our mixed oxide samples. The next step of our material development was the introduction of a secondary active metal. So in this case, we introduced cobalt as a secondary active metal, and we used different ratios of copper and cobalt in order to see its influence on the catalytic activity. Upon comparison of the catalytic performance, we saw that the cobalt-copper ratio of 2 gave us the best catalytic performance and therefore was chosen for the further studies. The next step of the material development was the use of is to investigate the influence of treatment temperature on the catalytic activity. So in this case, we used treatment temperatures between 350 degrees Celsius to 500 degrees Celsius, and we compared the catalytic activity of the mixed oxide obtained after the treatment at these different treatment temperatures. We saw that the 400 degrees Celsius sample showed us the optimum catalytic activity and therefore was chosen as our final material. This material was then further used to study for the stability test. So we did cycles of light-off curves between 50 to 400 degrees Celsius, and saw the change in the catalytic activity, notably the NO reduction yield, the CO conversion, and NO oxidation yield. And we found that the material was quite stable under the conditions that we proposed for the stability test. And then upon passing through the stability test, we used the material for a large scale synthesis because we are going to use it for a semi-pilot application in the future work. So for the large scale synthesis, we used a red laser reactor, and we shaped this LDH in the form of extrudes. And this is for the future work where the material will be used for a semi-pilot scale application. So this is under construction at Université de Mons. Currently, we are working on it to utilize the material that we prepared. beforehand with the shaping, and we will do the treatment, and we will try to see the difference in the lab scale and the semi-pellet scale application. Now we move to the third part of this presentation, which is the development of a kinetic model. So based on different literature studies, we found that the Langmuir-Hinshelwood-Hugen-Watson kinetics is the popularly reported kinetics for the reaction system. We have for the reaction system that is similar to ours. So what happens in the Langmuir-Hinshelwood-Hugen-Watson kinetics? So I will use LHHW as the nomenclature for such kind of kinetics. So let's say that we have a reaction called A plus B gives C, which means that we have reactant molecules A and B, which produces a product molecule C. So in the first step, we have the absorption of the reactant molecule A on the surface of our catalyst. In the second step, the second reactant molecule B that also adsorbs on the surface of the catalyst. In the step 3, there is an interaction between the A and B molecules that are in the adsorbed state to form the product molecule C, which is also in the adsorbed state. And in step 4, we have the resorption of this product molecule C. All of these steps, that is the adsorption, surface reaction, and resorption steps, could be a rate limiting step, and therefore can govern the reaction rate equation and therefore the rate of our reaction. So what was the methodology that I used for the development of the kinetic model for my reaction system? Was to first formulate the different elementary steps that are associated with the different reactions taking place in my system. Then determine the possible rate limiting steps for each of the reaction. Based on the rate limiting step, I derived the different reaction rate expressions. And I chose a reactor model in order to develop the differential equations that I would use for the optimization for the model parameter determination, and using adequate global optimization routine in order to find the parameters. So in our case, we developed 15 different mathematical models, which was based on different possible reaction pathways that were reported in the literature. So we used different sets of rate limiting steps that were possible for each of our reactions, and therefore we developed 15 different mathematical models. Each of these models consisted of 24 parameters, which are generally the model parameters, which is regarding the frequency coefficient, the activation energy and the factor. We used 70 sets of experimental data, which was obtained by changing the reactant gas composition at each time, and then getting the catalytic activity under different reaction conditions. So we gathered 70 sets of experimental data, which we use for the parameter determination for our case. For the reactor model, I used a one-dimensional plug flow reactor model in order to simplify the reaction model development and the parameter determination, obviously. And finally, I used the global optimization toolbox, which is generally available in the MATLAB software, in order to determine the model parameters we have in our kinetic models. So by using the whole steps that we see, we saw in the previous slides. So we had, I compared the correlation factor between the experimental model and the calculated, the experimental values and the calculated values of CO conversion, NO conversion, and partial pressure of nitrogen. And the higher the correlation factor, the better is the fitting. So in this case, I show you a 3D view of the different kinetic model forms and their correlation factors. So here you can see, for example, in form 11, we have a high correlation factor for CO conversion, 0.7 to 0.8 correlation factor for NO conversion. However, for the partial pressure of nitrogen, we have a very low correlation factor, which is less than 0.1. However, in this case, for example, in form 1, we have more than 0.9 correlation factor for CO conversion, NO conversion, and partial pressure of N2. And therefore, we chose that form one is the best fitting kinetic model for our purpose. So what happens in the form one? So in the adsorption state, as we saw before in the LHSW kinetics, that we have three main steps that is taking place. First of all, adsorption of the reactant molecules. So in the adsorption of reactant molecules, we have CO, carbon monoxide, which is adsorbing on the surface of the catalyst, with the adsorption of the NO in the form of the adsorbed NO state. We have the dissociative adsorption of oxygen, which is generally considered for the kinetic model. So where the oxygen adsorbs on the surface of the catalyst, but it dissociates to form atomic oxygen. And finally, we have the adsorption of water, which is again present in our system. So we consider its adsorption on the surface of the catalyst. For the form one, we have adsorption of CO and adsorption of NO from the adsorption step as the reaction, as the rate limiting steps. This next phase of the kinetic model was the surface reaction. So in our case, we have four different surface reactions taking place. The first one is dissociation of nitrogen monoxide. So the nitrogen monoxide dissociates to form the atomic nitrogen and oxygen. And we have a surface reaction between the adsorbed CO with the oxygen to form this adsorbed CO2. Similarly, we have the reaction between adsorbed NO species with the oxygen to form the NO2 in the adsorbed state again. And then we have the nitrogen formation, which is again by the interaction of the atomic nitrogen with the to form the adsorbed state of N2. So in this phase, we have the dissociation of nitrogen monoxide as the rate limiting step, which is generally considered a rate determining step for reactions between CO and NO. And in the final phase, we have the desorption of our product molecules. So we have the desorption of nitrogen dioxide, we have the desorption of our CO2, the NO2 and CO2 were formed by the oxidation reactions, and finally we have the desorption of our nitrogen. So upon comparing the calculated values of the CO conversions and the calculated value of NO conversion, which is with its experimental CO and NO conversion values, we see that we achieve a correlation factor of 0.9 and above, which is generally considered to be a good, moderately good fit, and therefore there has to be more development in the kinetic model in order to achieve higher correlation factor between our calculated and experimental values. Finally, we come to the end of our presentation. So some of the concluding remarks, we saw that the NO reduction by CO is possible under the industrial flue gas conditions using transition metal based materials, generally copper and cobalt as the active metals. We used a material development strategy where we use type of treatment gas, active metal ratio, and treatment temperature as the parameters to optimize our catalytic material suitable for the NO reduction reaction. We developed a reaction mechanism based on the literature and showed that the formation of the bind-dated carbonates during the carbon dioxide treatment facilitated the NO reduction reaction. Finally, I developed a kinetic model based on the Langmuir-Hinshelwood-Huygens-Watson kinetics, and we saw that the moderately good fit was obtained for the kinetic model with the experimental data. So what are the future works that could be done based on the work that I have developed during this research? The first and foremost will be the design of experiments. So during the design of, since our design of experiments was completely linear, it is important for us to have a very broad design of experiments where we can investigate the influence of the type of different treatment gases on the different temperatures for different copper cobalt ratios, and therefore it would help us to optimize our catalytic material better. The second point that could be investigated or explored is the optimizing the acidic and basic properties of our material by introducing different promoters, the alkali promoters like potassium or acidic promoters like zirconium. And finally, we can improve, as we saw before, we can still improve our kinetic model to achieve a higher correlation factor. And moreover, we can also expand our experimental data set in order to obtain a better, in order to help us in determining our model parameters better. This work was conducted in close collaboration with Région of the France and European Cement Research Academy. So I thank them for their technical and financial inputs. And thank you everyone for your attention. Now I'm open for the questions.
Thank you, Madan, for the summary of the main results of your PhD thesis. Je donne maintenant la parole à notre première rapportrice, Madame Valérie Chambon.
Thank you. Madam, for the last presentation. Firstly, I would like to thank again for the invitation, the script, and the presentation of this show. As I already said, we create defense, but I would like to say it again in front of this assembly. I enjoyed to read your manuscript, which is well written with a lot of pedagogy. And I think your presentation today is like your manuscript, performed with a lot of pedagogy, and it is very comprehensive for everyone. You discuss in your manuscript all results. All the assumptions are based on clearly explained facts. So even if your subject is complex, you are able to explain it with so I would like to congratulate you for both your manuscript and your presentation. We already discussed a lot about the results and the scientific aspect of your work during the private defense. However, there are some other questions and perhaps questions about the perspective more than real work and results you always do. But firstly, listening your defense today, I have one question. When you perform experiments in dry condition, you say that one of your assumptions is that you have a sort of water shift with no emission of hydrogen. Did you measure hydrogen, or are you able with your experiments to measure hydrogen? And how can you be sure that you are no hydrogen emission?
Yeah. So first of all, thank you for your question. So in our case, we are not able to measure the hydrogen, but based on literature, they say that the hydrogen production is really less in case of our system, because we have a lot of other components that would react with hydrogen. And therefore, even if we produce hydrogen, it will be less than 1 ppm and could be even less, which is next to 0. So we again assume that we don't have hydrogen. But if you ask, can we measure it with our system? No. Did we measure it during our experiment? No. And therefore, it's just an assumption.
And did you perform some experiments with the injection of hydrogen in a small amount, more than 1 ppm? But did you perform some experiments with a low amount of hydrogen in order to observe what is the results?
No, we didn't do it. Currently, we don't have the facility to do it, but the setup can be developed to do it. But currently, we don't have the facility to do it, and we didn't do it in our experiments.
And in in the real process, climate industry, what is the temperature of the fume where this catalyst or a catalyst could be introduced in order to perform the purification of CO2?
I'm not quite sure about the fume temperature, but I can say that the process that takes place at the cement industries are generally greater than 1000 degrees Celsius for the formation, for the decomposition of calcium carbonate into calcium oxide and CO2. So I assume that the flue gas that could come from the industries should have at least a temperature of 500 to 600 degrees Celsius at the outlet of the industry. But again, you have heat losses until you reach to a reactor or a capture process and so on. In our case, the reaction temperature is the maximum that catalytic performance we get is at 240 to 260 degrees Celsius.
So in the real process, you think that the temperature is higher than the one you tested?
At the exact outlet of the industry, yes, I think it's that, but I don't have a data. So this is my assumption based considering that we could have heat losses during the process, we can have heat losses during the transport and so on. So I assume that, okay, if the reaction is at more than 1000 degrees Celsius, we can have heat losses and can have the temperature of the flue gas at 600 and could be even less when we transport it to our CCUS unit or treatment CO2 purification unit and so on.
Okay, and did you test the catalyst at higher temperature?
The maximum we tested was 400 because our catalyst was treated at 400 only. So we stopped our reaction at 400 because if we go more than 400, we change the material of the catalyst as well. So we changed the material properties as well. Therefore, we stopped at 400, but the maximum that we can go with our setup at the lab scale is 500 degrees Celsius.
And in the pilot setup, I understand that it's able to perform experiments with it because construction is not finished during the work. Is it possible to work at higher temperature?
I think if I'm not wrong, we cannot go more than 400 degrees Celsius, 400 max with the heating jacket we have.
And you obtain a maximum of NO reduction activity of about 40%.
Mhm.
So do you think this activity is enough for an industrial application?
Generally, no. It is it depends again. It depends on the purity of the flue gas or the gas stream they need at the outlet of our CO2 purification unit. I'm not quite sure about the specification that the industry needs as an input to the CCUS unit from after the CO2 purification unit. But in general, just a reaction between NO and CO to have a 40% reduction is not enough. Therefore, we can either use this plus another reductant, like normally they use ammonia in case of industries. So we can have an additional ammonia addition to the reaction system to further elevate our NO reduction activity. And therefore we can ideally make it to zero, the NO concentration in our outlet stream. So yes.
And in real condition, you say at the beginning of the that you have SO2 fuels, don't perform any tests with these gases, but what do you think about the activity of your catalyst if you introduce SO2 to gases?
So in our case, when I see the literature, so for the materials like we have with the cobalt copper, generally the effect of the SO2 has not been found out to be very detrimental for the activity. There is surely a decrease in the activity, but it is less than 15%, 10 to 15%. but that is the maximum. But again, depends on the concentration of SO2 you have in your reaction stream. Yes, so we expect to have at max that, but we need to test in order to be sure, since our material, even if the material is not that novel, but the treatment process that we use make it more carbonate rich material, and therefore there are almost no studies who see the effect of the SO2 on such type of bulk carbonate species.
Because I know that SO2 is a problematic gas
Yes.
in the fuels, and SO2 can absorb on copper
Hmm.
paste,
Hmm.
and so after the activation,
Yes.
absorbed.
If I see practically, I think if we envision this at the industrial scale, I guess a treatment process to remove the SO2 from the flue gas can be installed before removing the NOx from the flue gas. So like a SO2 treatment process followed by a NOx treatment process, like that we can be sure that our catalysts don't deactivate.
In that case, all the process of treatment will be very important.
Yes.
If you have many catalysts or many processes.
Yes.
And actually, is there some process to CO2 purification in the cement industry?
In place already, like practically there, CO2 purification. The processes I know generally are there at the industrial scale, but specifically for cement industries, I'm not sure. But yes.
And at the end of your presentation, in the perspective, you say that it's interesting to improve your model with the introduction of appropriate elementary steps. What do you think? What do you mean?
Yes. So in our case, like the current model of our kinetics. So in this model, we consider, for example, water as an inert element. So what we consider is just the absorption of water, and it's competing with the common active sites with the other reactant molecule. However, we proposed, like, if you remember, we proposed a reaction mechanism as well. I showed it in the slides. So in that case, we assume that the water molecule doesn't only stay as an adsorbed state of water molecule, but also dissociates to form at least an hydroxyl group and an hydrogen group. So we need to consider the elementary steps regarding this dissociation step of hydrogen water molecule. And therefore, it is important to introduce this in our kinetic model. This would further increase the number of unknown parameters in our model. Therefore, it is very much important for us to even expand our experimental data set. So introducing new elementary steps with expanding the experimental data set is very much important, keeping in eye that we need to determine this unknown model parameters as well.
Thank you.
Thank you very much.
Congratulations.
Thank you very much.
for your work. I think I'm finished.
Many thanks. No, to Sabine.
Merci, Madame la Présidente. So first, I would like to warmly thank again Stéphane, Guy, and Christophe for the kind invitation to examine your PhD manuscript and participate in your PhD defense. And dear Madan, I would like to congratulate you on the quality of your presentation, which I found lively, extremely didactic, and nicely illustrated. So I enjoy it very much. And also, I would like to underline the great effort you have made to summarize and rationalize so much experimental work and complex kinetic modeling. So, in a very appropriate way, in your very nice speech. So, this is much appreciated as well. And so, the topic of your thesis was really challenging. Because I mean the selective catalytic reduction of NO by CO you did the reaction, you studied the reaction under real experimental condition, real reaction conditions. I mean, under oxidizing, CO2 rich and humid conditions. So, and this has been very little addressed in the literature. So this is a very, I mean, for me, you did quite impressive work during this PhD, doing this PhD. And also, I would like to stress that there are really many novelties in your PhD thesis that covers the development of catalytic materials, catalytic experiment under real reaction conditions, and also the challenging kinetic modeling. So, and also you investigate the scaling up of the synthesis of the mixed copper cobalt oxide material. I mean, you have addressed it at least in part, so this is also very interesting. And yes, as I already mentioned during the private defense, you have made consistent interpretations, which are supported by a strong bibliographic referencing. And you have really done an extensive literature survey, and it is really worth noting. So congrats again.
Thank you.
Well, in the future outlooks section, you have suggested to quantify the types of carbonate species in the mixed cobalt copper oxide materials. Yes, and you have suggested it to do it by Raman spectroscopy. So why this choice? And I mean, what kind of information do you expect to get with this technique to quantify the carbonate species?
Yes, so in our case, so the context of this study will be to see how much amount of bidentate carbonate species we have in our samples at different treatment temperatures. So quantification using Raman could be difficult because I understood that it could be difficult for the quantification, but XPS could be a good alternative to the Raman to use it. But in case of Raman, we could see some carbonate species for sure. Like for sure, we can see that, okay, if we have bidentate carbonates, but to quantify could be difficult. So it is just for how you call it, qualitative characterization technique. However, I further noticed that, okay, we can use other analysis like the elemental analysis, the CHONS, the show analysis, where we can get to know, okay, how much amount of carbon we have in our sample, and then extrapolate it to say, okay, that much, nearly that much amount of carbonates we have in our sample. That could help us to quantify. It may not be exact, but it could help us to quantify. And then we can see, okay, how it affects our NO conversion and NO reduction activity.
By using elemental analysis, you will not be able to discriminate between the types of
the species. No.
Sure. Yes. Yes, I know. It's always very difficult to characterize carbonate species within a catalyst. And I mean, do you know another technique that could be also helpful to better characterize the acidobasicity? I mean, the acidobasicity properties of mixed oxide materials, for example.
So normally people use ammonia TPT and also sometimes pyridine.
Also what?
Pyridine, if I'm
yes,
not pyridine.
Absorption of pyridine.
Yes, absorption of pyridine to determine the amount of acidic or basic sites. CO2 TPD is another option, but we already did a CO2 TPD on our samples. It's a little bit difficult because the problem is when you do a CO2 TPD and you go beyond your treatment temperature. For example, if we take a 400 degrees Celsius sample and we go for a TPD beyond 400 degrees Celsius, we have a huge peak of desorption of carbonates along with the desorption of CO2 from our basic sites, medium basic sites. So then it's difficult to quantify, okay, how much medium basic sites you have, or weak basic sites you have, or strong basic sites you have. So there is a problem in our bulk carbonate type of materials to use CO2 TPD. I'm not quite sure if we can use an ammonia TPD, considering the fact that the ammonia, I don't know if there is a reaction that exists between ammonia and the carbonates. because if there is a reaction with the carbonates again, it could lead to some other problems in quantification. So,
what do you think about using infrared spectroscopy with absorbed probe molecules to specifically characterize
yes,
the acidic properties
yeah.
or basic properties? There are specific probe molecules that can be, I think, helpful to be able to discriminate between these.
Yes, I didn't think of that. But I could go deeper into it. But we did one FTR spectroscopy. I'm not quite sure because again, it's a bulk carbonate species. So you have carbonate everywhere in your material. And when you do an FTIR, we saw really broad peaks for carbonates. And I don't know if we can go further with the technique that you explained, but I didn't go further into it, so I don't know really. Yes.
There are some papers in the literature, some
Mhm.
papers in the literature that can be helpful. For example, using an FTR with the propene as probe molecules to better characterize the basicity of materials. So
Mhm.
just a suggestion. And
Yes, please, I'm listening.
take your time. And also with respect to acido-basic properties, but of perovskite materials. I don't know, it's the same, I still have a question about the mixed oxide materials.
Mhm.
So can you tell us a bit more about the influence of the nature of the promoters?
Mhm.
So at the end of your presentation, you suggested, of course, I can fully understand the use of alkali metals like potassium ions that can improve the absorption of the reactant
Yes.
molecules. But you also suggested to use zirconia or zirconium at least
Mhm.
as an acidic promoter. So what do you expect from
So
this promoter?
basically, for alkali, that we will improve the basic properties, but with the acidic properties like zirconia, we can have the copper zirconia interaction. So you have the copper O zirconia species, and these are generally the oxygen species that are easily reducible and can be exchanged or can form oxygen vacant sites in our samples. So therefore it can help us. However, having high basic properties in our materials is also not very good, because if you see in our flue gas, we also have a lot of carbon dioxide. So if your sample is too much basic, then it will start absorbing more amount of CO2 on its surface. And again, you have an interaction or a competition with the reactant molecules. So it might or might not help in your reactions.
Okay, so the idea is to find the balance between acidic properties based on the CR or zirconium-based
Exactly.
ions,
Yes.
and also to take benefit of the oxygen storage capacity of such elements.
Exactly.
Perfect. I would like to come back to the perovskite section, even if you didn't present anything during your presentation. So what was the main reason for studying the feasibility of perovskite materials as catalyst for this reaction?
Okay, so generally I first explored a very extensive review of perovskite materials for NO reduction by CO reaction. So I saw that, okay, perovskites could be a good alternative for our mixed oxides as well, because generally perovskites are more stable than the mixed oxide because they are calcined at high temperatures. So generally, and our reaction temperatures are lower than the calcination temperatures. So we expect not to have a lot of differences in the material properties during the reaction. So we could expect a good stability for our material. So we explored perovskites. However, we saw that there is a literature gap. We don't see a lot of literature studies under industrial flue gas conditions again. So it was again interesting for us to see, okay, if perovskites are active or not. And we saw that the perovskites activity was comparable to what we got with our mixed oxide samples from LDH. And therefore we say, okay, the perovskites are a good alternative, but we still need to work on it to again optimize the material composition and so on. So I guess it is more playing with the material composition than playing with the calcination temperatures, because generally at temperatures higher than 600 degrees Celsius is required to reach a perovskite structure. So it is important for us to maintain that temperature, but at the same time, use different metals. Active metals could be copper, cobalt, manganese, iron, and sometimes other materials at the A site or the B site, or form some oxygen vacancies by reducing the amount of A site cations and so on, which could affect. So we have a lot of parameters that we can play around in order to get an optimal point of catalytic activity.
So you first investigated, how to pronounce in English? Stoichiometric, I don't know. I mean, with the cobalt one, for example, and then the lanthanum deficient perovskite. But you demonstrate that the NO reduction activity was far less than the one obtained with the mixed copper cobalt oxide,
yes,
in this case. And then you studied the influence of copper as a secondary B-side cation, starting from a perovskite with an extremely low specific surface area.
Yes.
Because you investigated the influence of copper with the lanthanum deficient perovskite. So what was the reason why you started from the perovskite with the lanthanum deficiency and not directly from the stoichiometric
yes
LaCO3 perovskite?
So in our case, when we saw normally when you have a different deficiency at the A site, you can create some oxygen vacant sites in your materials. This oxygen vacant sites, the literature studies show that the oxygen vacant sites can be fruitful for reactions that we have. Therefore, we said, okay, maybe the less amount of lanthanum in the material with cobalt is not helping us in the reaction, but maybe introduction of a secondary active metal in the site, in the B site, can help us to improve the catalytic material by forming oxygen vacant sites at the same time. That's why we went into that field just to see how it is, and yes, and compare the catalytic performance for different cobalt copper ratios again. Yes.
But I think it would have also been interesting to start with the pure LaCO3 perovskite and then introducing copper.
Yes. As I told you before, we have a lot of parameters.
Yeah, sure. This is not
so
for the future.
Then it will
maybe
be
for the next PhD thesis. Of course, I mean, this chapter about the perovskite can be viewed as a prospective study with new perspective on the use of such kind of materials for this specific reaction, especially under flue gas conditions. So this is absolutely good. Yes, and then in the future outlooks, you have proposed to study the effect of adding a low amount of noble metal from the platinum group metals. So what do you expect from this? Why do you suggest to add a few amounts of such kind of element?
So when we studied the perovskites with the transition metal oxides, we saw that we don't get enough catalytic activity that we already saw in case of the LDH pre-mix oxides. So in that case, so we said, okay, normally noble metals are really highly active for NO reduction activity, especially the COSCR. Therefore, I suggested, okay, let's put some noble metals in our perovskites. Depends on the methods of, then again, it depends on the method of preparation. Either you put certain PGM materials like the palladium inside the perovskite structure, or you put it as a deposition on the perovskite structure, and you see the effect on the catalytic activity, just in order to improve the catalytic activity. But it also depends, like if you put more, you may or may not get a good activity, but at the same time, you have to keep in mind that if you put more, then the cost of your material increases significantly as well.
Exactly. Because I'm fine with your answer, of course, but for me, this seems to me a bit contradictory with what was mentioned in the thesis objective, because also you reminded in your presentation that you wanted to prepare, I mean, cost effective catalytic materials, especially in view, I mean, of an industrial or industrial scale applications of the not only the catalytic reaction but also the preparation. Yes. Yes. And in your opinion, which perovskites, in terms of composition, could be more resistant to SO2 poisoning?
Iron-based, most probably, because if I remember correctly, the reference, they didn't prepare perovskites, but they prepared wet impregnated sample. So they had copper, I guess copper, iron, and either cobalt or manganese. So they had three active metals deposited on titanium dioxide. So and they saw the effect of nearly 100 ppm of SO2 in the reaction medium, and they found that the sample with iron showed better activity even in the presence of SO2. Therefore, I would suggest iron could be a good metal to introduce in the perovskites as well. Just to see this.
It has been already mentioned that iron is inert to SO2. So
Yes.
Good suggestion. Yes. Yes, and in view of scaling up and shaping of catalyst, do you have any idea about how to shape perovskite materials? Because for the LDH, you started, you prepare paste, and then you shape it.
Yes.
But for perovskite materials, do you have any idea? Any suggestions to make?
I never thought about it, but there are different. I guess if we can use the conventional methods, the first one, to use any binders that we generally use in case of shaping, we can use some adequate binders for that. The second one could be a deep coating. So basically use a good support like an alumina or something, and you just coat the perovskite on the surface of your support. The third one, I don't know. I'm not really sure if we can make the same process like we did with the LDH with the perovskites as well. We never tried it because it's not a conventional method to do with, because in our case, the shaping was done without binders. So the shaping was done without binders, which is generally not a conventional method to do it. So we don't know if it is still possible with the perovskites, but it's a good dimension to look into. Yes.
So I think I should stop here. But first, I would like to congratulate you again for the very nice PhD thesis.
Thank you.
And also for the quality of your manuscript and the presentation as well. And also for the discussion. I mean, because for me, you fully demonstrated that you have acquired a great knowledge of the topic.
Thank you.
So congratulations.
Thank you.
Thank you. Thank you. No, it's your turn, Thierry, for some questions.
Yes, I have not much in fact, because Professors Chambe and Madan stole my question.
Oh.
I'd like to have a little word to the public, because I go, of course, I'm in line with the comments of Professors Chambe and Madan regarding the quality of the work. But also it's important for the real life, I would say. You have to imagine that thanks to people like Madan, we are going into the good direction. And he did it with a remarkable talent, because it's not easy at all to have this capacity to integrate a very complex subject with so many capabilities and fields of expertise, because he has to think about it at the microscopic level. So he has done it in terms of synthesis, in terms of mechanisms, suggestion, and modeling. And this is very complicated. So usually that would be 3 theses separate with very specific expertise, but you managed to do it in a very convincing way. So that's one thing. And the other thing is your ability to communicate it, and we have seen it very clearly. It has been a very good presentation. And believe me, with time we see presentations that are less good, but yours was really at the top level. So thank you, Madam. Anyways, I have some questions. A few remaining questions, yes. So regarding the cost effectiveness of the noble metal-based catalyst, I'm not completely in line with Professor Madan, because we have examples like like for the for the reaction between ammonia and oxygen to produce nitrates. So that's noble metals pure taken, and of course the TWC catalytic converters. So I would like to go a bit further, and in line with the question of Professor Madan, what would be the role, or how many atoms of palladium or say noble metal would you put at the surface of your catalyst in terms of number of atoms per square meter?
In general, or you're speaking in?
No, in this case, I would say, because it's a concern. Of course, you cannot do it in a classical way. You have to deposit them and not precipitate them in a single step. Otherwise, you will lose so many noble metal atoms that that will not be achievable.
Okay, I'll try this because I don't have expertise in the deposition thing, and also with the platinum PGM group metals, but we normally consider to have low amount of noble metals on the surface. So I would assume like 2 to 3 atoms per centimeter square of the surface, centimeter square from the area.
Oh, I would say a bit more.
Bit more.
Yeah. So that drives me to a very complicated question that I have. What would be, regardless of platinum whatsoever, what would be your definition of an active site for the CONO reaction in your case? How would you define it? There's no clear answer to that, but what would be your
okay, let's take a conventional material. Any general material, not conventional, any general material, catalytically active. So in that case, the active site for the NO is the one where it can form the surface intermediates. So that is the nitrate species, and at the same time have oxygen vacancies that would help it to decompose. So the main concern in such reactions is to how to help the nitrogen monoxide to break its bond. So there are 2 options. Either you use certain active reactant molecules like hydrogen that can help us to dissociate this bond easily, or you use oxygen vacant sites where the nitrogen monoxide can easily break to form, which at the same time oxidize the surface and form atomic nitrogen. But for CO, again, there is an ambiguity in the which surface is active for the CO. So it's mainly depends on the reduced surface. For example, in platinum, we have the CO poisoning because you have the platinum species. So you have the CO poisoning. So I can assume that we can have the same amount type of active sites in our sample as well for the absorption of CO. But again, the CO, that is again, it has to react with the oxygen molecule. So either the oxygen comes from the lattice, which is easily removable, or you have an oxygen from the reactant stream. So it's something like that. But the active site is generally, so I'm talking this in reference with the copper, because generally the copper plus is generally considered to be active for the CO. But again, there are studies where they say, okay, no, the Cu2 plus species also is active, but unanimously they consider that Cu plus is active as well, is active for the CO absorption for sure.
Yeah. So finally, this is not a solved question, and it's not very soon that we'll have a solution to that question. But anyways, you can still report converted molecules or formed molecules per square meter. And this is perhaps the next question that I have. did you try to normalize your conversions or your conversions per square meter of surface?
No, we didn't. I didn't do it. The conversion as in the during the catalytic activity conversion, you mean?
So yes,
Yeah.
yes. Because I was wondering on the synthesis. In fact, yeah, I had another question, but close to that. And when you upscale your synthesis, do you still have the same surface, or do you have a
In the same range? Not exactly the same, but in the same range. Like at the lab scale, we have around 65 meters square per
Yes.
gram, while in the large scale we have around 90 to 95, if I'm not wrong, 90 to 95.
So when you upscale, you have a better
Surface area. We have a better surface area.
Do you have an explanation or a suggestion?
There can be various factors, because if you see in the chapter, I mentioned that to upscale, we change the concentration of the metal nitrates, we change the amount of the carbonate amount remained the same, but the concentration in the solution changed. So I don't know if that really affects, because we really make sure that we have enough carbonates and we are at a good pH for the formation of the NDH. So I don't know if the other factors would have helped in
But
improving.
in the two scales, you still have HDL.
Yes, HCl formation. We did an example.
That's fact.
Yes, if you can see on chapter 5, if I'm not wrong, last scale. So we did an XRD for each step. So we did a lab scale that we did here. We did another lab scale at the place where we were making the large scale synthesis before actually doing the large scale, and then we did a large scale one, and we did it in 2 batches. So we did the XRD for both the batches, and we get the exactly same difference.
Yeah, so that kinetics
I don't
limitations or concerns
Yes.
when precipitation occurs.
Yes.
I've done more or less the same observations in persons. So I think I don't have very much time, so I would like to take an excessive time for me. So I think I will stop. Yeah. Oh. Yes, I had the basicity and the acidity question in line, but I think you gave a very convincing answer. So it's okay. I think it's yeah. I will stop. Thank you.
Thank you.
So thank you, Madan, for this nice presentation. So the first thing I will do is to acknowledge you and your supervisor for the invitation to come today and to participate to the evaluation of your work. It's a great pleasure. As I mentioned during the first defense, the quality of your work is very, very good, in my opinion. For a PhD starting on this topic is not simple, because you want to do reduction in the presence of students. So, but you succeed, and there is a lot of very nice results. Some you already published, but probably others will come. And you have very good quality for the writing and for the presentation. The first presentation you performed on defense was very nice, scientific presentation, and this is completely different. So you make an effort to try to communicate to the people what you did, and this is not simple to do. So felicitations for that. And now I have a few questions. Continuation of the previous question, in fact. The first question I have is about the kinetic approach that you developed. Okay, so you are specialized in chemical engineering. So you developed genetic model for the reaction. And when you discussed about reducibility, because you presented some TPR, your presentation was, your discussion was based on consumption of hydrogen and temperature of reduction. But do you think it would be possible to develop kinetic model to extract, for example, activation energy of copper reduction or something like that, to be able to compare really the reducibility of the element in the materials in terms of kinetics?
I think yes, but just not with TPR. I guess we need to be sure that which material, which species we form in our material during the TPR. So maybe some other characterization technique combined with TPR can be used to be and to ensure that we have that species, and then we know some of the reactions that takes place, like the copper reaction with the hydrogen, the copper species reaction with the hydrogen, and we can use it to determine the parameters. Yes, like vaguely, I think yes.
Because I don't remember. I think it was in the beginning slide. It's possible to go back to your TPR slide at the beginning. Because so you see, we discussed already a little on that to say, okay, sometimes the shape is not so different, and if you see the contribution of each species you identify, it's completely different from one to another. But you know that initially you have just copper plus.
Yes.
Right? Sure.
Yes.
Yes. So it means that if you take the beginning of the reduction, probably you can just start from this beginning part and extract some kinetic law just to have the exact activation of copper in the different materials. After, of course, it becomes too complex. But just for the beginning, it would be possible. Yes?
I'm just trying to correlate between the equations that we generally used for the model parameters, like at the end of the day, it's the RNAs plot that we use to determine our activation energy and the correlation factor or the factor. And if we see that, so we need to change the temperature, but at the same time, we need to know how much of hydrogen has been consumed. So if we measure at the end of the TPR, yes, yes, and yes, should be possible. Like right now, yes, but maybe when we do the calculation, could be certain difficulty. But yes.
We discussed a little about the oxygen vacancy, etc. And when you work on oxide catalyst and when you are doing redox reactions, it's a parameter that is important. And people often refer to Mars and von Clausen mechanism, for which you will have steps of reaction that are not exactly the same than in your model.
Yes.
And my question was about the choice of the model you use. It's Langmuir-Hinchelwood. Why did you select Langmuir-Hinchelwood instead of trying to model a redox mechanism involving, I don't know, reducibility of copper?
Yes. So basically, the choice of the kinetic model was really based on the already published results of Langmuir-Hinchelwood type of kinetics for such kind of reactions. It's not the exact reactions, but normally, for example, as Thierry already mentioned about the TWCs. So in TWCs or three-way catalysts, they normally use Langmuir-Hinchelwood type of kinetics for the development of the kinetic models. And since we have similar kind of reaction system, so I chose this Langmuir-Hinchelwood kinetics to develop the equations for my reaction system. So this was my starting point, because obviously there are different kinetic models that can be used, because there are some publications that show just a simple power law expression, or kinetics can also help them to correlate with the experimental data, while there are some who propose Ehlers-Riedel type of mechanism, which is just like a sister kinetic mechanism of Langmuir-Hinchelwood. So There are some mechanisms like that, but it is well demonstrated in case of Langmuir-Hinshelwood for our case of reaction system. So I used it as a good starting point. But obviously we can try to explore new kinetic models, which is again a hefty task, but it's not possible in 3 years. So
Yes.
we have to start from somewhere.
No, you're right that probably it's a good model, except that in three-way catalysis, in fact, you have metals.
Yes.
When you have metals, probably the mechanism is a little bit.
Mhm.
So it's a discussion. You mentioned just the precision for me. You mentioned formate the spaces in the mechanism, right?
Yes.
And this is observed experimentally
No, it's a proposition. It's not a.
because it can be observed by infrared.
Again, the problem is with the carbonates.
Ah, yes. Yes. So this is what is the question. Remember.
We tried it.
We try. Okay. I have another question regarding the mechanism. Yeah?
Mhm.
So you perform your modeling, and from the modeling, probably you identify a rate determining step.
Mhm.
What is the rate determining step in your case?
In my
What is the rate determining step in your case with this catalyst?
Yes, the rate determines. I showed it. I guess maybe I was not clear, but I will show you. Check. So in my catalytic model, the adsorption of CO, the adsorption of NO, and the dissociation of NO were considered as the rate determining steps in my kinetic model.
Okay. So that when you are doing the reaction, just one step is limiting the rate, not three.
Exactly. But we have 3 different reactions taking place in the system. So we take rate limiting step for each of this main reaction as a rate limiting step.
Okay.
So in order to have a overall
Okay.
reaction rate.
So, but if you take the reaction globally,
Mhm.
the enter of the reactor and the outside of the reactor, which one of the 3 is limiting the reactions? It's
It
not
depends
possible to
what
determine.
we are seeing. It depends what we are seeing. For example, if you want to see NO2, so you have to first determine which reactions lead to NO2 production. In our case, the NO2 production is led by the reaction NO oxidation by NO oxidation reaction. So NO reaction with oxygen to form NO2. So we try to first find out which step of this reaction can be rate limiting. And then when we say, okay, the rate of production of NO2 can be determined by the rate limiting step that we have. In this case,
Okay.
absorption of NO.
Okay. So if your objective is to perform the reduction of NO to N2, the limiting step is the dissociation of NO.
Yes.
Okay. So do you think applying kinetic model can be a predictive tool to help to the modification of the catalyst composition?
The problem with the kinetic model is the model parameters changes with the material composition.
Yes. So in fact, you can say, okay, my model said, okay, my problematic finally is to activate dissociation of NO. So I will modify my catalyst according to this conclusion and just adopting the agent or method to favor dissociation of NO.
Yes, but you can already determine it from the drift studies which have already been reported in the literature, because they all say we need NO decomposition. So it's like in general, yes, but if you want to use the kinetic model to prepare new materials, it's difficult. For that, you have to go to, again, the modeling tools that they normally use, machine learning and AI. You have to go into that space to help you to determine which materials you can take. But again, you need a vast experimental data set in order to be sure that you are getting a good material composition proposal from the model. Yes.
Maybe I will just ask a last question. For you, what is the most important for architects? Activity, selectivity, or durability?
Can I choose more than one?
You can select two.
Cost.
No, it's a rare question because when we are in the laboratory, generally we are looking for activity. Activity is the most important for us. And when you are discussing with industrials, it's completely different.
Yes.
Activity is not a problem.
Yes.
And the cost is not a problem too, depending on
Who is
the other properties. So for you, what is the most important feature of the application?
For me, the most important is activity and durability. So, because with the selectivity, we can have less selectivity but a more durable material. So, like that, we are sure that at least we are going to have this activity over the time. And for me, I'm thinking from an industry point of view because they don't want to change their catalyst very frequently or regenerate their catalyst very frequently. So durable for sure. And when it has a steady activity, it is good. Like it depends on the application, but steady activity is good. For example, to be to adhere to the different norms. For example, if you have a NOx, this much ppm of NOx you can have at the outlet of the flue gas. So they have to ensure that you always have less than this boundary. So it is better to have something that has a consistent activity and durable for sure.
Yes. So durability is very, very important.
Yeah.
Okay, thank you for
Thank you very
your
much.
answer and the discussion.
Thank you.
Thank you. André?
Thank you, Mrs. Chairwoman. So, Mr. Behera, dear Madan, you already received a lot of congratulations today, and I guess it's not finished. So be prepared and enjoy for your work, the whole of your work, for the manuscript, your communication, well, your deep understanding of the subject. And I will insist on your today's presentation. A few weeks ago, after the private defense, we suggested that you prepared a new version, more pedagogical for a wider public, and you really, really did that very well. So congratulations for that again. Now, just one question for me. You have shown that one important point was what we can call the reducibility of the surface. So the capability of the surface to act as a reductant in a chemical reaction. And depending on for instance, the ratio between copper 1, copper 0, copper 2, or cobalt 2, cobalt 3, for instance. And so this is important when trying to understand what happened during the thermal treatment under controlled atmosphere. So what we can call an activation step,
yes,
between synthesis and the normal use of the catalyst. So supposing that you choose the right or the best thermal treatment, can we really imagine that this characteristic will remain unchanged during the process, during normal use of the catalyst, knowing that the chemical composition of the mixture, the gaseous mixture, will change, and therefore its redox potential as well, making these ratios change with time. So you tested the activity of the catalyst for a few weeks, but well, isn't there a problem? Is that an issue, or do you think it's not a problem at all?
No, there can be an issue regarding the change in the reducibility of the materials in the catalyst over the time. So in that case, that's why it's better to have a long duration experiments, which they normally use. However, there are some methodologies that people follow in order to predict what could happen in their materials over the time, so that they don't have to do long stretch experiments. I don't have a deep understanding of those methodologies, but I know there exist certain methodologies that help to do it. The third thing that is like, even if there is a change in the material composition, like the species change and stuff, over the time, maybe you decrease your activity, but at some point you stabilize your activity. Let's say you decrease the activity by 15%, but you stay at this new level for a long time. It is sometimes possible, and we saw in our case as well, when we did cycles of sleight of curves, at one point the yield was almost stable. And so we saw this could be a possibility as well. So there are different various possibilities. And if it happens, there is change in the properties. There is again another option of regeneration. So you need to have a good regeneration methodology or a protocol that would only help you to regain your active sites, but also
the second part of my question.
Yeah.
Anticipated. Okay.
Yeah.
Okay. So we can quite easily imagine that it should be possible to regenerate
Yes.
the surface, supposing that there is no carbonate or sulfate or sintering phenomena. What would be interesting, but probably should it be difficult from an analytic point of view, is to be able to measure these ratios between, for instance, copper 0, 1, and 2 after the thermal treatment, after using it for a while, or after regenerating. Can you see some technical solutions for that? To achieve that?
In order to know what you have, generally, if you want to have a surface analysis, you can do an XPS after the treatment, before the after the treatment, and after the treatment and after the test. So that is possible just to see the change. There have been a publication beforehand from our lab where they showed what is the effect before and after the test under dry and wet reaction conditions. They tried to see the change in the amount of oxygen in the samples, so the lattice oxygen and adsorbed oxygen in the samples, in order to see the variation in the ratio and its effect on catalytic activity. So generally, it's possible.
Is it possible to meet the ratio of the
metals? Yes.
Yes. Okay. In different oxidation states?
Yes.
Okay. So, okay, this will really be interesting to understand what happens during the thermal treatment and.
Yeah, because in general we use we can imagine to use yes, no, the XPS. No, I was thinking of TPR, but I was like no. But yes.
Okay, thank you.
Yes,
sure.
Thank you. So, seeing it's my turn. So, dear Madan, I will not be really original, but I want to address to you my sincere congratulations for your challenging and very consistent work achieved with different difficulties. The first one is, as already mentioned, many bricks, scientific bricks in your work with the experiments at micro-pilot scale, micro-reactor scale, the development of kinetic modeling, which was very ambitious, with 15 possible pathways, the reflection at the micro-pilot scale. So congratulations for that. Another difficulty was the fact that it's a co-supervised thesis with a duration of, I think, three and a half. So medium between a French thesis and a Belgian thesis. Okay, with administrative constraints, with 3 directors, with the specific demands, and also a thesis achieved during the COVID period. So it's an additional difficulty. It was really a pleasure to work with you. For example, for the development of the kinetic modeling, as you have always a positive behavior. I want to highlight this, always smiling, it's really a pleasure. As already mentioned also, many thanks for your pedagogical presentations. and always different, for example, for the different comités d'accompagnement de thèse. In the Congress, we were together in Toulouse for the Société Française de Génie des Procédés, and you presented your speech in French. It was, yes, you succeeded, you did it.
They just little aspect.
It was fantastic, and I appreciate really the nice graphically illustrated slides.
Thank
And also, finally, a work completing the development in the Equator. So, in the framework of the Equator, you addressed in your work the purification for the oxy-combustion process. So the oxy-combustion. So really, really challenging and really successful. Perhaps a simple question about the microparallel scale for a future work, for future PhD student or postdoc, I don't know. What would be the challenges with such device, with such apparatus? What will be the challenges? What is your opinion?
Okay, so there are some operational challenges and some, I would say, scientific challenges regarding the catalytic material. So the first part will be the operational challenges. For example, in our setup, we tried, but we were not able to get composition from an oxy-combustion plant. For example, have a high amount of CO2, but in our setup, we were not able to % of CO2 in our system, reaction system. So it would be better to see how we can manage to have more amount of CO2 in our system on the catalyst. So this is what we can look for modification of our process. And there could be other further modifications like Madame Chambert already proposed, like to see the inclusion of certain reductants like hydrogen that could help us to improve our catalytic activity. So that can be modified in our system. And also, finally, we can try to modify the lines to be adequate with ammonia. Why? Because we can use ammonia as a reductant as well. Industrially certified process of NO reduction using ammonia. So it is better for us to see how we ammonia as a reductant, and by promoting both NO reduction by CO and NO reduction by ammonia in the same process. And adding the operational challenge, material challenges, yes, there is always, like the first part of the first point of my future perspective in this presentation, I already mentioned that it is important for us to have an extensive design of experiments in order to optimize the material properties adequate for a high catalytic performance. In our case, it was very linear, it was very direct, but it's important to see effect of each parameter on the catalytic activity. So it is important for us to have an extensive design of experiments, which would again need more time to do the experiments, but it will give us a clearer picture of the material composition that is perfect for our reaction system. The second part is more about introducing new material combinations. Like I propose to use manganese and iron that we didn't use it before. We did some wet deposition materials, but it didn't work. But we never tried with good LDH derived mixed oxides to see its effect on the catalytic activity. So according to the literature, the manganese and iron along with copper can be a good mixture for the catalytic performance. Therefore, it is important us to explore that area. And again, we can also see the effect of different synthesis processes on the catalytic activities. because it is important for the industry to have a simple material development process, because for example, there are certain catalytic processes that may or may not be developed in that industrial scale yet, and therefore there is always a challenge to improve the TRL of our considering the material production process. Therefore, it is important to choose the material production process of a synthesis protocol that would be cost effective for the industry as well. So to see this effect on our catalytic activity could be a good dimension for a project. Yes.
Okay. Lot of work.
Yes. 3 PhDs and a postdoc.
Many thanks, and once again, my sincere congratulations. I give the floor to the three co-directors. The first one from the wrong side, Guy.
Thank you. Yeah. Yes, first I would like to say thank you to the member of the jury, external member, Valérie, Sabine, Thierry, Sébastien, Diane, and André. Special thanks to Valérie and Sabine as rapporteur of the manuscript. I know they take more time to write the report, but I think it's important to improve the quality of the manuscript. The first discussion and the first presentation could help us to improve the manuscript. Thank you very much for this. And also thank you to come two times, because it's a Belgian specialty to have two defense, but normally they take not a lot of time for the second one, to have time to drink and eat something. Okay. Second thing, I would like also say thank you to the ECRA, to the technical and financial support, and also to the Région des Hauts-de-France for the French part. And I would like to say also thank you to the UMONS, because they also give a part of the Madan grant. It's important to have the external support to perform good work. I would like also say a word about the part of the experimental part. Unfortunately for you, Madan, you have the double pain. The first one is the COVID. The second one is the increase of the price, the disponibility of equipment, and the delivery time increase. Sometimes they multiply 1 month become 4 months, become 8 months, and unfortunately we have a finish time to finish a PhD. This gives me the opportunity, perhaps without a second PhD or a third PhD, we can try to exploit some result, especially on the kinetic models, because you work a lot in this field. I think it's a good idea to find a solution to exploit it, and also to support my group to start the measurement, because the installation is more or less finished to start the measurement. Okay, I would like to say, as Jan mentioned, it's always a pleasure to see you. You come in my office with a big smile, always. Sometimes I say, okay, Madan, I have a big smile. 7 o'clock. Yes, I don't come back at home. Really. But it's always a pleasure to see you and to discuss. It's a pleasure also because we discuss something, and 2 or 3 days after I receive the documents. As a good engineer, sometimes you do 80–90% of the task fastly, but sometimes we need to take more time to see in details, but I know well because all engineers are more or less the same to try to do it fastly to reach more or less the objective. But it's a real pleasure to discuss with you, and not only in the scientific part, but also the human part. And I think when we are a small research group, it's very important to have a good guy in the team. And you are a good guy. And I don't prepare as the end of my document. I try to don't forget the thing that it really a very pleasure to work. And finally, the presentation. Clearly, it's a real pleasure to attend your presentation, as a lot of jury members say, and Diane also say for the Congress. You asked me in the beginning, I can try to do it, the presentation in French. I'm sure you were able to do it, but it's an additional difficulty. Is not necessary for this kind of work, but clearly you are also, it's very impressive to see your French progress in only 3.5 years. I see some people in my group during 10 years and are not able to speak in French, but you, yes, and well. And today is very impressive. When we discuss 5 weeks ago, something like this, you say, yes, the important thing, no, your subject is complex with a lot of equations, a lot of scientific difficulty, because I say you work on the materials, on the mechanism, on the modeling. Unfortunately, perhaps on the technical and apparatus, you can also present the results, but clearly it's difficult because we give the lecture and to try to give the key message. And when you see the slide, it's a very good idea to take a lot of time to prepare a very good presentation. And I can say only thank you for the work, and good luck for the next part of your career. Yes. Last word. I would say thank you, especially to Christophe, because Jan say 3 supervisors met only 1 day per day. It's very important to highlight the work of Christophe.
Nice transition, Christophe.
Thank you. So, first of all, yes, I will again thank the member of the jury for evaluating your thesis twice finally, with the private one and now with the public one. And so thank to them. Also, I will also thank the funders, and the financial support is very important for us to work finally. So thanks to them. And Madan, you have been and you are a great person to work with. Really. It should be noticed also that when you arrive to the labs, finally you nearly didn't know anything about catalysis, and you work a lot. You work really a lot to develop your knowledge by reading papers and books and so on. And when we heard today again the jury members, we heard that you are a specialist in catalysis now. So it's really a good work. And yes, it's due to your personality, always smiling. reactive to comments and suggestions that we make during our exchange. You're also a force of proposal to make evolve of your subject of the thesis. For example, you go to Marco Daturi labs, you also contact Thierry to go there and work maybe with. You have not only been involved in your thesis also, because you help also other students, for example, developing some models and so on. You already prepare finally the arrival of a new person, because last week you were synthesized new catalysts from your ideas. So it's a good thing. So really, I wish you to find a new contract soon, and maybe we can work together again. Congrats.
Thank you, Christophe.
Last
Thank
but not
you
least,
again. Everything was said.
Already said.
Very difficult for me, but
Make a good
thanks
summary.
again. Every people in the jury agree to review Madan's work, and especially so Valerie and Sabine for the manuscript, and also thanks also for Diane, Thierry, Sébastien, André for the following also of the Madan's works, also because with the CSI, for example, synthesis of materials and so on. So it was interesting, and of course it's also interesting to work with Belgian teams, also for the future, maybe with indirect works again. It was also a pleasure for that. And also, like Guy, I want to thank Christophe for the good work he managed for Madan, and said it was a pity that he was only an invited member in the jury, because we have some administrative problem with our doctoral school. So it's some problem, but you are with us. And so to end, of course, I want to congratulate you, Madan, because it was really a pleasure to work with you, but not only working, because you're really a good guy, and it was interesting to have you in the labs for everything. So I wish you also all the best for the future, and also to collaborate again and again. So thanks again.
Thank you, Stéphane.
Ok. Je pense qu'il est temps maintenant, oui, de nous retirer pour délibérer.
Okay.
À tout de suite.
À tout de suite. I want to thank my
Félicitations.
Merci.
Chère Madame, C'est une thèse en cotutelle. Évoquer le texte pour l'Université de Mons, ainsi que pour celui de l'ULCO. Alors, pour l'UMONS, après avoir pris connaissance de la thèse déposée par le candidat, entendu le candidat en séance privée, conclu à la recevabilité de la thèse en vue de l'obtention du grade académique de docteur en sciences de l'ingénieur et technologie, le jury réuni sous ma présidence a entendu ce jour la défense publique de la dissertation originale, après quoi il a décidé à l'unanimité de conférer à monsieur Madan, Mohan, Behera le grade académique de docteur en sciences de l'ingénieur et technologie. L'ULCO, c'est plus simple.
Ouais.
Et il n'y a pas de suspense, puisque du côté de l'ULCO également, à l'unanimité, nous avons tous décidé de décerner, je cherchais le bon terme, le grade de docteur de l'Université du Littoral Côte. Donc, à nouveau, félicitations. De grade. Il n'y a plus de grade, mais as a good guy, a good speaker, a good scientist, nous voulions tous t'adresser vraiment profondément nos félicitations pour tout ce que tu as réalisé.
Merci.
Voilà, nous voulons dire. Et enfin, dernière chose, mais là, c'est toi qui vas travailler. Tu dois lire, si tu le désires, le serment de jeune docteur.
Je connais pas par cœur.
Prends 3 pages.
Pour les suivants, il faut apprendre par cœur.
Et,
C'est en anglais.
C'est long, ça.
Oui, c'est
non, mais il découvre, en fait. Je découvre, là. Il savait pas.
Si.
Ah, tu le savais?
Ah ouais,
Ok, ça va. Quand même.
Donc, il y a mon ami.
Il y a un peu de lumière.
Ah non, ça c'est bon. J'ai commencé en français.
Ah, comme tu as
Ou l'un ou l'autre, on peut les deux.
Il y a deux langues.
Non, il faut le faire.
T'en fais un des deux, fais-le en anglais, c'est plus vite.
Do it in English.
Ou alors,
Just...
tu parles bien français.
On a bien, mais on comprend.
Oui, mais on attend le pot. Allez, Madan.
So in presence of my peers, having completed my doctorate in semi-theoric physics analytic and having thus practiced in my quest of knowledge, the exercise of demanding scientific research by cultivating intellectual rigor, ethical reflexivity, and respect for the principle of scientific integrity, I commit myself for what will depend on me in the continuation of a professional career, whatever the sector or the field of activity, to maintain an honest conduct in my relationship to knowledge, my methods, and my results.
Oui, tout à fait, c'est celui.
C'est la signature du.
Oui, on doit. Oui, ça doit encore être signé par le recteur, mais on prend directement la signature du jeune docteur. Ouais. Et donc, il ne faut pas le perdre.
Forme de foi. Donc je dois.
First of all, I want to thank the jury members of today's defense and who have also been there during the private defense as well. Thank you very much for your comments, for your suggestions regarding my manuscript. It was really good and it was really insightful for me. And it's really a new perspective to the current project. It's not only for me, but for the following student who will be coming up in this project. And it will be a great pleasure for him or her to start the PhD with a new perspective and a dimension. So thank you everyone for the valuable comments. I want to also thank Andre, Thierry, and Diane for being a part of the continuous evaluation process.
during the CAT and CSI meetings. It was really important for me to understand because, as Christoph already said, I didn't belong to a background of catalysis. So it's very much important to know what does a scientific communication or what does a science expects from a catalyst expert or a material expert. So it was very much important for me to understand what kind of results someone expects or what kind of questions someone should ask regarding such kind of for certain scientific explanations and so on. And thank you very much. It really helped me to shape my manuscript that you have today, and everyone has commented, had good comments regarding the manuscript. So some part of this comments also goes to you because you helped me to shape the manuscript as well. A special thanks to Diane as well, because I worked with Diane very rigorously for the development of the kinetic models, and it was really a pleasure to learn about the kinetic models and so on. And we know we had a lot of tough times to decide what to take, what not, how to decide models and so on and so forth. And every time it was becoming complex. So we had to funnel down our knowledge and our decisions so that we could present something that is very much comprehensive for the public, both scientific and general public as well. So thank you very much, Diane, for the support, and it was really good. A special thanks to Sebastian, because I worked with Sebastian a lot during my PhD as well, and he was really nice is a very naive word, I would say, but he was really supportive in making me understand what the materials could be. And he was always proposing me, okay, maybe try in this dimension, or maybe think in this dimension, and so on and so forth. And we could make some good characterizations and results. We could publish some of the results, and we are in the process of publishing more results. So thank you very much, Sebastian. It was always a pleasure to work with you, and I hope to work in future with you as well. Thank you very much. Now I want to come to my supervisors. Guy, we'll start with you in the chronological order like this, just to not mess around. So it was really a pleasure to work with you. So it's for me, if you see the thesis, it's more both scientific and engineering. So it is very much different, the mindset of people from a chemistry background and also people from the engineering background. And it was very delightful to talk to you, to know what does an engineer want or what questions can an engineer ask. And it's also important for me to find solutions or answers to those questions. And it's always important for me to learn that. And thank you for being that mentor for me and helping me grow that mindset during my PhD. And it was really a great honor to work with you. Thank you very much, Pete. Stefan, and I spent my first year in ULCO, and I interacted with Stefan a lot. We discussed a lot of aspects of the thesis. Yes, but also we discuss a lot of aspects about the administration. We know it's a little bit tricky sometimes, but Stefan has always been very supportive in whatever I needed, like anything, any help regarding the administrative or any simple task like opening a bank account. He was with me to go with me to the bank and help me open a bank account. It was a time when I spoke no French. Rien. So I spoke no French, I understood nothing, and he helped me in everything to make me feel comfortable in this lab. So I want to thank Stefan for being that kind to me and being very supportive during the thesis as well. Thank you so much. And finally, Christoph. So I guess the most amount of time I spent in this thesis was discussing with Christoph, because we almost had meetings every day. So formal, informal meetings, but we had for sure in the lab, discussing what could be the results. Sometimes we are always curious to have a good new material and see a result that we never expected. And then we brainstorm what could be the reason for such kind of activity or such kind of experimental results. And it was really really insightful to discuss with you, because because it's good to know someone that we are both in the same space of not knowing the things and have the curiosity to know it. And it is always good to find people like you who help people like me to grow in this field. So thank you very much, Christoph, and I owe you a beer. So I owe you a beer to Stefan, I owe you a beer to Christoph as well. So thank you very much. And to the people from the lab, from both the labs, can you come here? I can't move. So this is my small family I have in France and Belgium. And these people, I will not name everyone. I know I have a very bad memory, so I will miss someone and I don't want to do that. So everyone has equally contributed to what I am today, emotionally, physically, and mentally. So thank you very much, everyone, for being that kind to me. It's for me, even if I'm an étranger, you never, even if I was a foreigner, you never made me feel like I'm an outsider. You always welcome me like a family, help me every time, everything I asked for. And the only thing I could do is bow down. Thank you very much. Finally, my family who is online, I guess I can. Okay. I hope they are still online. So I want to thank my sister, my brother-in-law, my parents, my mom and dad, for being here to witness what I have achieved so far. And it's very difficult to meet them because they live so far away, and not they, I live so far away. So it's very difficult to meet them, but I know they are always being my emotional and mental support every time. And this one is for you, Mom and Dad.
Oh.
Thank all my friends who could join via Zoom. Unfortunately, they were not here, but they could join via Zoom. And I want to thank them as well, because I know sometimes when I was stressed, I used to call them, eat their head and brain, and they used to be really supportive of me, supportive towards me, and it's really good. Thank you very much. Thank you very much. Thank you very much, everyone.
Picture
of Rania.
Oh, the member.
Yes. Yeah, we click it here. Yes, with this.
On pourrait faire.
Pour ce photo.
Avec les encadrants.
Yes, but I don't want to shadow here.
Voilà. Comment le mettre?
And we have a small fork, Indian fork outside. I don't know how to call it in English now.
Il parle bien.
Oui, il parle bien. D'habitude, c'est voilà nos yeux, moi.
C'est une sacrée délégation.
Tu sais, souvent, tu vois.
J'ai vu de loin.
Salut. Salut Renaud. Oui, ça fait un peu de temps. Notre voyage à Liban. C'est la dernière fois qu'on s'est vu.
Bien arrivé, oui, pas de problème de grève.
Non, on a trouvé des solutions. Jusqu'à présent, ça va.
Elles sont bien ici, elles ne veulent plus partir parce qu'elles sont bien ici. Ah. Ça, c'est quand on est dans
le